All right. Hello, everyone. So today we are going to be discussing question number 4 from the January 2014 Mathematics Comprehensive Exam. This question is all about minimizing and maximizing a multivariate function on a specific region. So the question reads, let D be the set of points x, y, such that x squared plus y squared is less than or equal to 100, and let f of x and y be 3x squared plus 3y squared minus 12x plus 12y plus 10. And it asks us to find the absolute maximum and the absolute minimum of f on D. So in order to do this, we need to consider the extreme value theorem, or at least the multivariate version of it. And it states that the absolute maximum and the absolute minimum, if the function is continuous, can occur at two different types of places. The first one is critical points. And the second one is boundary points. And if you know the one-dimensional version, right, of the extreme value theorem, you'll sometimes hear these be referred to as endpoints. But now, because we're working in higher dimensions, there might be an infinite number of them. They aren't necessarily endpoints anymore, right? So that's why we call them boundary points. Cool. So let's tackle our critical points first. To find all the critical points of a multivariate function, we need to do something a little bit more complicated than just taking the derivative, because we know that taking the derivative of a multivariate function involves partial derivatives. So we're actually going to compute the partial derivatives of our function f. So the first one, let's go in order. F sub x, or the partial derivative of f with respect to x. You also might sometimes see it be denoted as partial f over partial x. It's really the same thing. And the way that we find this is just take the derivative and we treat y as if it were a constant, right? So the 3x squared is going to turn into a 6x. That's just the power rule. The 3y squared is going to totally disappear, right? Because that's just a constant. The minus 12x is going to turn into a minus 12, right? And then everything else is going to disappear as well. So now to compute f sub y, or the partial derivative with respect to y, we do the same process and we're going to get 6y plus 12, I believe. So we've got 6x minus 12 as our partial derivative with respect to x, and 6y plus 12 as our partial derivative with respect to y. And the way that we're going to find the critical points is by setting both of these things equal to 0 and solving for values of x, y that satisfy both equations. So let's set both equal to 0. And it's very clear, right, from this system of equations, that x is going to be equal to 2 and y is going to be equal to -2, right? And because these are unique values, we can say that 2 comma -2 is really, right, our only critical point of this function. And obviously, because 2 squared plus -2 squared is less than 100, this is going to fall within our region, so we can accept this as a possible absolute maximum or minimum. So this is our only critical point. However, we can also now focus on boundary points. So now I'm going to say this is BP, and I guess just going back up here, this is CP. Awesome. Okay, so for our boundary points, there's actually a couple different things we can do. The first thing is we can take our boundary equation, which would be x squared plus y squared is equal to 100, right? And then we can plug that equation into f to substitute it and turn it into a function of just one variable. However, here, right, that's going to involve plus minuses because this is a relatively complicated equation, and it's best to just avoid all of that. So the way that we're actually going to proceed is using a type of method called Lagrange multipliers. And Lagrange multipliers I'll talk about in a second. Let me just write this down. Lagrange multipliers are ideal for finding maximums and minimums along or subject to a certain constraint, which is what we have here, right? Our constraint that x squared plus y squared is equal to 100. So let's just rewrite f of x, just so that we have it down here. So f of x is going to be 3x squared plus 3y squared minus 12x plus 12y. And it's either plus 10 or minus 10, plus 10. Not that it really matters in the grand scheme of things. And excuse my handwriting. This is a y. I don't really know how to fix that. There we go. All right, so now let's find our constraint, which we actually already did, right? That's going to be x squared plus y squared is equal to 100. And the reason I don't do less than or equal to is because we only care about the boundary, which is where they're perfectly equal, right? Awesome. Okay. So basically, right, Lagrange multipliers say that we have an extreme value when this equation is satisfied. The gradient of f, right, which is just a vector of partial derivatives, don't be scared of that symbol, is equal to lambda, which is some constant, times the gradient of g, which is our constraint. Cool. So all we need to do is compute the gradients. Now, the gradient of f is going to be easy to find, right? Because we already have the partial derivatives. The partial derivatives are up here, 6x minus 12 and 6x plus, or 6y plus 12, right? So 6x minus 12, comma, 6y plus 12, that is going to be the gradient of f, right? We just throw the partial derivatives into a vector, and that's going to be equal to lambda, which we don't know what lambda is going to be yet, times the gradient of g. So how do we find the gradient of g? It's a function of two variables, right? X squared plus y squared minus 100 is equal to 0, right? That's our constraint. We just have to compute the partial derivatives of that equation. So the partial derivative with respect to x is clearly just going to be 2x, right? We treat y like it's a constant. And with respect to y, it's just going to be 2y. So now we're going to equate the components of the vector to get that 6x minus 12 is equal to 2x times lambda, and 6y plus 12 is equal to 2y times lambda. So this next step is a little bit tricky, but we're going to have to solve all values of x, y, right, that satisfy this, where lambda is a constant. So the way that I would go about doing this is by solving both of these equations for lambda and setting them equal to each other. So that's precisely what we're going to do. When we do that, right, we are going to get 6x over 2x is just going to be 3. And then 12 over 2x is just going to be 6 over x. So 3 minus 6 over x, that's going to be equal to lambda, right? And then next we have something very similar. It's just going to be 3 plus 6 over y is equal to lambda, right? Awesome. So with these two equations, we can set them equal to each other, and we see that 3 minus 6 over x is equal to 6 over y, right? Or in other words, because we can just get rid of those 3's, negative 6 over x is equal to 6 over y. Awesome. So I'm going to actually pause the video, but what you would do is you would go into your boundary equation, right, and solve for that. I don't want to do the math out, but I'm going to do all of this out, and then once I have a solution or several solutions for x and y, I will get back to you. All right, you guys, I am back, and it actually was not that bad of math. I was just being dramatic, right? So if we know that negative 6 over x is equal to 6 over y, we can very definitively say that negative x is equal to y, provided that they are not equal to 0, right? And then what happens is we can just substitute negative x in for y into our constraint, right? to get that 2x squared is equal to 100 and solve to get that x is equal to plus or minus 50. And depending on which value that is, y is just going to be the inverse value, the additive inverse, right? So that's going to leave us with two solutions, right? So that is going to be positive root 50 and negative root 50, as well as negative root 50, positive root 50. So let's come back. Let's come back and consolidate, right? All of what we have so far. So we have 2, -2, right? As well as these points. And these are going to be the points to test, right? Because we want to see which one actually results in the maximum and the minimum value. These are just the extreme values. We're not sure which one is the absolute maximum and the absolute minimum. So what did I say? I said 2, -2 or something like that. Yeah, 2, -2. So that's going to be the first one that we're going to test because it's easier math. And then we're going to do the square root of 50, negative square root of 50, right? As well as negative square root of 50 times square root of 50. Okay. Oh, and this is a negative sign. I'm just not really good in terms of my handwriting, but that's okay. Okay, so let's test 2, -2 first. And the way that we're going to quote unquote test it is by plugging these points for x and y into our equation, 3x squared plus 3y squared minus 12x plus 12y plus 10. So let's do that. So I'm going to once again write it because I don't want to keep scrolling up. So that is f of xy, sorry, is equal to 3x squared plus 3y squared minus 12x plus 12y plus 10. Okay. So looking at this, right, we can just take 2 and -2 and plug them in for x and y. We know that -2 and 2, both of them squared is just 4, right? So that's going to be 3 times 4. F of 2, -2 is going to be 3 times 4, plus 3 times 4 again, right? Minus 12 times 3 plus 12. Oh, nope, not 3. Sorry. 12 times 2 plus 12 times -2. That's going to cancel, plus 10, right? So that's just going to give us 34, I believe. Now, it's a little bit trickier with the square root of 50 and the negative square root of 50, right? F of, let's say, 2, -2. But let's compute that anyways, because why not? AKA, we have to. Okay. So that's going to be 3 times, what is the root of 50 squared? That's obviously going to be just 50, right? Plus 3 times 50, right? And then minus 12 times root 50 plus 12 times negative root 50. Again, those are going to cancel, right? Plus 10. Okay. So that is just going to be 3 times 50 is what? 150. So 310. And to find f of negative root 50, root 50, okay, sorry for that awkward pause. For some reason, my screen stopped sharing and I wasn't sure how to fix it, but we got everything under control. Essentially, right, what you're going to see is that you're going to get the exact same value when you plug in negative root 50 and root 50, right? Because these two things are still going to cancel each other out, right? It's going to be plus and minus this time. And then, yeah, these two things are going to be squared. So you're just going to get 310 again. So as we can see, we have an absolute maximum value, which is going to be 310, and an absolute minimum value, which is going to be 34. And if you wanted to leave your answer just like this, that would be absolutely acceptable. So there you go. That is how to find the absolute maximum and minimum of this function, right, subject to a certain region.